Hey aviators, now we're going to be talking about how the engine works, the electrical systems, how our instruments work, our pitot systems, and our vacuum gauges. However, you're in luck today because you're actually going to be viewing and taking a sneak peek of an instrument course. The instrument course is exactly the same thing. We go over the same exact thing. So to prevent me from starting all the way from scratch and show you the same exact thing, so if you take your instrument course after this, you're gonna be like, wait a minute, didn't we go over this already? Well, technically, it's literally the same thing. So without further ado, let's go ahead and look at that instrument video and let's get started. All right, so starting off with the pitot system, I'm going to explain what this is. This probably looks like a mess right now, but don't worry, we're gonna go through it together. Over here, this is actually representing the pressure and the altitude. So down here, let's assume this is 29902. All these dots in here are representing the air molecules. The air molecules are going to be very important because all of these instruments literally go off of this, and I'll explain this in a moment as we're going through through these three instruments. This right here is going to be the inside of the instrument, representing the inside side view-ish. Right here, and then these little squiggly little things, these are AeroNerd wafers. All of them will have AeroNerd wafers, and we'll explain what those are a little bit more in depth in a minute. And then on the over here, this is going to be the actual instrument that we're looking at while we're in the cockpit. This right here, this little circle right here, this is going to represent the linkages to the AeroNerd wafer to the dial. So with that all being said, let's go ahead and start right into the, let me get my little airplane here so I can so how the airspeed indicator works. So this is our airspeed indicator, our altimeter, and this is our vertical speed indicator. So starting off with our airspeed indicator, how it reads is this AeroNerd wafer will expand the more air it is being pushed into it. Where does it get its air from? Well, it gets its air from the pitot, the pitot tube. Oh gosh. It's coming from the pitot tube. Now, the more air, the faster it's going through. So here's our airplane, the faster it's going through the air, and let's say it's down here. We have a lot of air molecules down here, right? And so that lot of air molecules is being pushed in here. The faster the airplane goes, so the faster we go, the more that this AeroNerd wafer is going to expand. Let's say right here, let's say it's 50 knots, and over here is, I don't know, let's say it's 100 knots. So let's say it expanded out 100 knots. We're going 100 knots. Let's say this is like down here somewhere. 100 knots, cool, yay. Now this is at sea level, okay? Now what happens when we get 100 knots full of air molecules in here? However, when we start climbing, look what happens. We're getting less and less and less air molecules. Now let's say we level out here and we're still going 100 knots. However, our indicator is going to represent that we're going slower if we don't have our static port connected. Why? The less air molecules that we're getting, the more this is going to decrease and decrease and decrease. And then our airspeed indicator is going to show that we're going like maybe 50 knots, or our indicator is going to be 50 or 40, because it's only getting 1 or 2 or 3 molecules, so it's gonna feel, it's like, okay, well, I'm not getting that much air, so I must be going very slow. So okay, cool, I'm going to tell the airspeed indicator needle to read 30 knots. However, you got your static port right here. When this is connected, the static port says, no, you idiot, you idiot, we're not going 30 knots. The reason why you're reading 30 knots is because we're up at 5,000 feet or 10,000 feet. So obviously we're not going 30 knots, so you need to fix yourself. So then the pitot static goes, oh, okay, well in that case, we're not going 30 or 40 knots, we are going 100 knots. Cool, thank you, static port. So that's one of the reasons why we have to have a static port inside of the part of the airspeed indicator. The static port is connected to the outside of the instrument, and then the AeroNerd wafer is connected only directly to the pitot tube. So that is why the airspeed indicator has to be connected to the static port. Also, with that being said too, let's say that we have a blockage. Let's just have we have a blockage right there, and we're zooming down and going down, and what happens when this gets blocked? Well, if you guys says it's gonna freeze, I don't think it's gonna freeze. It's actually gonna go to 0. Why? Is it gonna go to 0? Because what happens to all the air that's in here? it's going to leak out of the drain hole. It's got a drain hole right there. So this is going to go all the way back to 0. Another thing too, when the airplane is on the ground, it's literally the same thing. It's your airspeed is reading 0 while it's parked, it's tied down. The pitot tube is not getting any air rushing into the pitot tube, so it's literally the same thing. So it makes sense. That's another analogy that you can use of why it goes to 0 if you just have the front of the pitot static, the front of the pitot block. Now let's say we're going 90 or 100. We got it all out here. Now let's say we have this and this blocked. Then what's going to happen? Now if you're saying that it's going to freeze, you're absolutely correct. It will freeze. Now the tricky thing is to understand what happens when you climb and descend. So what's going to happen is this pitot tube is going to say, hey, let's say we're down here, for instance, at 1,000 feet. And so all of this is at 1,000 feet. We got 1,000 feet worth of air molecules in there. Now as we climb, we're going to get less and less and less and less. So what's going to happen is you're going to have less and less air molecules up there. And what's going to happen to this aneroid wafer? You don't have as much pressure pushing or holding that aneroid wafer together. So what's going to happen is it's going to expand. So what happens when this expands? This is going to climb, because it's thinking that once this expands, it's thinking that it's getting more air in here. So our airspeed indicator is actually going to act like an altimeter. Let's say vice versa. Let's say we go back down. Let's say we're here and we go way back down. So we're adding a lot more pressure in here. Way more pressure. Now we got a lot more pressure compacting this aneroid wafer. And what's going to happen to that aneroid wafer? It's going to really compact on itself, right? And what happens when the aneroid wafer and the airspeed indicator contracts? It's going to go down. So that's why they say when you go down, this is going to go down. When you go up, this is going to increase. So your airspeed indicator is going to be a backup altimeter. So that's the functionality of that. All right, moving on to the altimeter. The altimeter is a very basic instrument, and knowing how it works and all. So it has an aneroid wafer that's sealed with standard pressure. So 29902, I don't know if you can see it. 29902, my horrible handwriting. That's going to be sealed in here. Now, just like how we did the example up here, when the airplane starts to climb, so it has a lot of pressure. So let's say it's down here, has a lot of pressure. All this pressure is in here. Cool, yay. Pressure's in here. Now, when you start climbing, you have less and less air molecules, less and less pressure. This is going to have less pressure compacting that aneroid wafer. So what's going to happen is this, just like if you let a balloon up, it's going to expand and expand and expand. Same thing here. This is going to start expanding. When this expands, this is designed to link to the altimeter needle and showing it a climb. And the more that expands, of course, the more this altimeter keeps moving. And the same thing when you go down. When you go back down, you have a lot more air molecules in here, more pressure compacting this aneroid wafer back down. And when that happens, this aneroid wafer shrinks, which causes the altimeter to go back down. All right, so now we're going to be talking about the VSI, vertical speed indicator. So this aneroid wafer is connected directly to the static port. Now, when we climb, this is going to be directly toward it. So let's say we're at 299.2, we're at sea level. So all of this is going to be equal, right? It's equal. Cool, yay. Same exact thing. Now, once we start climbing, our static port is going to be directly connected to the inside, only the inside of the aneroid wafer. So what's going to happen as soon as we climb, we're going to have less pressure in here instantly because we're climbing. Now we have more pressure on the outside of the case, so what do you think is going to happen? This is actually going to shrink. When this does shrink, this is going to show a momentary climb. And I say momentary, why do I say momentary? It's because this right here is a little itty bitty hole. It's also connected to the static port called a calibrated leak. And all it is a small hole. That's all it is. So all of the pressure in here it wants to equalize, right? So, but it can't equalize because it has to go through this small little hole. So while it's equalizing, this is going to show a climb until it has the same amount of pressure, and then this AeroNerd wafer will reset itself back to its normal, and then when that happens, this will go back to normal. Same thing in a descent. When you have a descent, when you go down, you're going to have a lot more pressure in here. So what's going to happen to this? You have a lot more pressure, and you have less pressure out here. So this is actually going to expand. When this expands, this is going to expand. It's linked to the VSI needle, telling the needle to go down. Now, all of this pressure is wanting to go into equalize this lower pressure, right? High pressure always wants to go toward low pressure. So it's going to slowly come in here until it is equalized, and then when it is equalized, then it's going to go back to 0. And that is how the pitot instruments work in a nutshell. Okay, so now we're going to be talking about the gyro instruments. They work off of the suction of a vacuum, engine-driven vacuum pump. So here's our vacuum pump up here, but let's start from the bottom up here. Next time you jump in your Cessna, look underneath your rudder pedal. So here's your rudder pedals right here. There should be a little white filter down there. That's where the air actually comes into. It's actually getting sucked in from there. So from there, it goes up through these instruments, goes through a vacuum suction gauge, so it actually reads the vacuum, and then it keeps on going out because it's being derived from the engine-driven vacuum pump, and then it disperses it off into the engine cowling. Every aircraft's different, but that's generally how it's going to work. When the suction goes in through here, this is your heading indicator. Now this is going to be, let's say we have like little scoops. So we have little scoops right here. There are little scoops, and then we have this little there. So the air is going up through here, and when it hits this scoop, it's going to rotate this way, and then it's going to keep rotating and rotating and rotating, and that's how the gyros are going to work. Your heading indicator is going to be a vertical. It's going to spin vertically, so it's going to be rotating off of the horizontal plane, which is up and down, and then your attitude direction indicator is going to be spinning on a vertical plane, so it's actually going to be spinning horizontally. So this one's spinning this way, this one's spinning up this way. Now speaking of gyros, there's two principles of gyros, which is rigidity in space and precession. So rigidity in space is going to be a very important one for these ones. So rigidity in space, what this one does is, let's say that it is, I'm just going to use my phone here for example. Let's say that it is, here's the here's the plane, and there's the gyro. It's spinning just straight up here. So when the airplane is actually moving, this does not move. It's still spinning in the same exact direction. So now I'm flying this way. It's still spinning this way. When I'm flying over here, it's still going to be facing that way. So when it does, it's actually rotating on this plate. And when that happens, this is actually connected to a bunch of linkages and linkages that makes this actually rotate. Now there's a really good video that actually explains. They have a really good computer graphic representation of exactly how all of this works in a Embry-Riddle video, a special VFR. I'm pretty sure a lot of you have already seen it already, but I highly recommend you look at those videos too to really explain this, because they can explain this way better than I can. So I really recommend, and I'll probably put a link on the video up above so you can actually see this a little bit better than I can explain actually. So that's literally how the heading indicator works, and you can actually also adjust it too. So if your heading indicator is going north, and so here's your heading indicator right there, the gyro's right there, you can actually disconnect the gyro, and you can actually move the gyro itself to a certain rotation, to a certain position and direction, and then you can re-engage it. So now when you're turning, it can actually show the accurate heading. And again, go into that video that I recommended before. They can explain it way better than I can. But that's how we can actually use that little knob, and we can actually adjust it when we are facing east and our heading indicator says that we're facing north or whatnot. So that's how that one's going to work there. Now the same exact thing with the attitude direction indicator. It is spinning this way, so you have a horizontal one spinning this way. So and this is again rigidity in space. So if this is like this, actually I'll just use this. So when this is straight like this, and we are actually turning our airplane, this is still straight and level. So when it shows in our aircraft, oh, it shows a bank. So just think of it, this is always going to be straight and level over the horizon, does not move. Our plane moves around these instruments. That's another way how you can visualize it too. Some of these ADIs have what's called pendulous vanes, and that actually prohibits or prevents the ADI from actually tumbling. So if you bank more than 60 degrees, you ever get in one of those Cessnas and the attitude direction indicator is just tumbling and tumbling and tumbling. Well, they have this pendulous vanes, which actually prevent that, and whoever invented this was a genius. So this actually has to do with precession. The precession is the force is going to act 90 degrees from the actual where the force actually originated from. So what that means is, let's say we have a wheel that spins this way, we have our rotation spinning this way. Okay, so say we apply a force here, we're not going to feel it until it's here, until it's 90 degrees from the from its original point that you felt it from. So that is literally precession. So that principle being said, let's say this gyro is spinning this way. See, the arrows are spinning this way. Now this is a little door that is preventing air from pushing outwards. Why do we want that? So let's say that we are about to tumble. We're banking and tumbling. So this is still rotating this way, and we have a bunch of air. Now this pendulous vane door actually opened up, allowing this air to be pushed out. And just like how we mentioned before, here's our rotation. Here's our rotation, and we applied it here. We're not going to feel it till here, right? So if we apply it here, 90 degrees is over here. So if it's pushing out this way, it's not going to be felt until it's right there. What's going to happen? That force is going to push this back this way until it's back upright again. The door is automatically going to close due to gravity, and then it's back to normal again. That's how the pendulous vanes work. Okay, and finally we have the turn and slip coordinator. We have this one. Now this is a gyro that is not run by a vacuum pump. This is actually DC. Why do we have DC and another one versus another one being powered by an engine-driven vacuum pump? Well, because of redundancy. You know, if one system fails, then we get another backup. So this is actually DC power. That's why we have a little DC right there. We have our little airplane here. We got our standard rate turn ticks, and we have our little ball right there. Cool. There's a little plane right there. Cool. So how this works is this actually on a canted gyro. So what that means is the gyro is not perfectly horizontal. It's not vertical. It's actually at a little angle right there. And this is so you can actually feel. So if it was horizontal, let's say if it was horizontal and we started to yaw, we would be going on the same rotation, the same axis. So it really wouldn't sense anything, right? And let's say if it was vertical, just vertical, it would be able to sense our yaw, but it probably wouldn't be able to sense our roll at all, really all that great, right? So to fix that, we have a canted gyro. That way it can tell when we turn and then we yaw, it kind of resists the little motion, so it can actually sense our quality and our bank angle from the canted gyro. So that's literally how that one works right there. This right here, this little ball inside of here, that does not work off gyro. That is just a ball that's filled with fluid. So and if we are turning, the ball will automatically just go this way just due to gravity. That's literally all how that works. Another way how you can visualize of what your airplane is doing. So here's a ball right there. Look at this ball as the tail of your airplane. So Here's your ball is perfectly centered, you're nice and coordinated. Now, if you are going, now your tail is way out here. That's why they say to step on the ball, because if you put right rudder, that's gonna get you back centered again. So that's another way how you can visualize what your plane is doing by looking at that turn and slip indicator.